Okay.
You can go ahead with your presentation.
Thank you.
Yeah.
So, first of all, I'm going to present my work titled Novel Rotor Fault Diagnosis Method Based on Robust RLMD. And wait a minute. And Hilbert Transform Technique. First of all, I'm gonna introduce myself. I am Asma Guedidi, PhD doctor in the Department of Electrical Engineering at Biskra University in Algeria. I received the Renewable Energy Master degree in 2016 from the University of Biskra and my PhD this year. My research interests include condition monitoring and fault diagnosis in electrical machine using advanced signal processing and machine learning. Before delving into the details, we must at least highlight the great importance of induction machine in the industrial section. A synchro machine is omnipresent in various industrial sectors such as aeronautic, nuclear power, chemistry, or even transport, and this is due to multiple advantages such as low cost, simple construction, efficiency, and robustness. However, despite these advantages, these machines are still prone to various faults. For this reason, the scientific community has been asked to find solutions to these kinds of problems. As a result, a new engineering science has been raised that called the condition monitoring system for industrial equipment. The objective of this science is to design automatic fault detection and diagnostic technique to avoid any heavy economic losses and increase the availability of production system and reduce the cost of their maintenance. In fact, condition monitoring has three major tasks, which is supervision, protection, and diagnostic. This latter is compromise detection and localization as well as quantification of the faults. Prior to delving into diagnosis technique, it is essential to address the failure impacting three-phase squirrel-cage machines, including their source and their classification as shown in the following table. This table presents the different faults that encounter the induction motor related to their origin. We can observe here that the broken rotor bar is considered among the internal electrical that occur in the induction motor. In fact, this fault is frequently considered the most formidable task due to various factors, such as broken rotor bar have the lowest order harmonic that are close to the fundamental frequency. The harmonic related to the fault caused by broken rotor bar exhibit remarkable sensitivity to changes in load levels, resulting in corresponding fluctuation in their positions. There are a lot of causes of broken rotor bar that can include by manufacturing defects, mechanical stress, thermal stress, and aging and wear. On the other hand, there are a lot of symptoms of broken rotor bar that can be an increase in vibration, noise, imbalanced current, reduced efficiency. This will represent the rotor with 1 and 3 broken rotor bar defects experimentally. This equation presents the signature of broken rotor bar in the current spectrum, where G represents the sleep and F represents the fundamental frequency. In order to study the effect of different faults, multiple studies focusing on fault diagnosis have led to the development of harmonic estimation technique. This technique can be categorized into two groups, non-parametric method and parametric method, where the non-parametric method is further subdivided into frequency analysis and time frequency analysis, while the parametric ones is subdivided into subspace method and linear prediction methods. Unfortunately, the classic strategies fail to diagnose the faults under non-stationary condition, which complicate its implementation and therefore reduce the reliability of the detection task, which require us to look for another detection strategy. To overcome the aforementioned problems, the objective of this work is based on developing a new diagnosis strategy method using advanced signal processing based on the recent and novel method that's called the robust local mean decomposition combined with Hilbert transform. The proposed strategy is dedicated to the diagnosis of Rotor fault regarded as the most challenging fault to detect in induction motors through simulation environments. Before delving into the details, we must at least point out an overview of the proposed method. The robust local mean decomposition is an adaptive signal processing technique used for multi-component signal separation and demodulation. The method overview is defined down below. Robust local mean decomposition is an improved version of the local mean decomposition. It applies a set of optimization strategies to address boundary condition, envelope estimation, and shifting stopping criteria in the local mean decomposition. Robust local mean decomposition simultaneously extracts monocomponent signal referred as product function and their associated demodulation signal, amplitude modulation, and frequency modulation signal from a mixed input signal. The principle of the proposed method consists of evaluating the instantaneous component relative to the fault feature obtained from the robust local mean decomposition analysis of the envelope signal as presented in the following step. After the acquisition of the stator current, the signal will be subject to Hilbert transform first to obtain the envelope signal, then will be subject to robust local mean decomposition pre-processing to extract the fault indicators. Why using the envelope as a diagnostic signal first? So technically, this equation presents stator current signal and its envelope. We can observe here in the red cycle that the envelope of the stator signal contains a continuous DC plus the main information of the fault, which denotes as 2 key SF, the signature, the frequency signature of the fault component related to the Rotor bar. This is why we use envelope as diagnostic signal. Simulation results. Basically, the mathematical model used to generate the stator current is well described in the references 9 presented in my paper, where the motor is a star connected 3 kilowatt machine with 4 power and 28 bars. The motor was supplied by 3-phase 50 Hz sinusoidal balance supply at the rated voltage amplitude of 380 voltage. The current signal is sampled at the frequency of 10 kHz. The proposed algorithm were implemented in Matlab and tested using simulated signals. Our goal is to efficiently extract the instantaneous characteristic, amplitude, and the frequency of the fault from the stator envelope signal under variable conditions. This photo presents the simulation result of the stator current signal and its envelope, where the envelope is colored by the red and the stator current is colored by the blue for a healthy state and for a faulty state. We can observe here in the faulty state an occurrence of an oscillation that confirms the presence of a fault. We'll study here the impact of the fault severity. This figure presents the resulted decomposed subsignal by the application of the robust local mode decomposition to the envelope current signal, which is, we can see here that the first product function copy the original form of the original signal, which can be considered as the most dominant subsignal that reflect the fault indicator. Here, this figure presents the frequency modulated signal and the amplitude modulated signal of the resulted from the decomposition after the application of robust local mean decomposition. We can observe that only the magnitude of this technique that gets affected by the fault severity, while the frequency magnitude modulation signal doesn't get affected by the fault severity. This figure presents the instantaneous frequency of the most dominant product function obtained by Hilbert transform and the instantaneous frequency amplitude of the dominant product function obtained by the application of Hilbert transform, we can confirm that only the magnitude that varies accordingly to the fault severity. Here, we'll study the impact of the load values on the results. This figure presents the stator current and its envelope with a load variation at the time reach 1 second. We can observe here an increasing in the magnitude of the signal accordingly to the load variation. This figure presents the decomposed subsignal obtained by the application of robust local mean decomposition to the envelope current signal. We can see that the most dominant product function varies accordingly to the load variation compared to the previous research regarding the fault severity. Here we present the instantaneous amplitude and frequency of each product function obtained by robust local mean decomposition. Always the first dominant product function that gives an indication of the fault and load effect. Here we can observe that the most dominant product function varies accordingly to the load variation. Here are more details follow, which confirm our results. The instantaneous frequency of the dominant product function obtained by Hilbert transform increased accordingly at the time reach 1 when the load varies. And here the instantaneous amplitude obtained by Hilbert transform increase accordingly to the load variation. This paper investigates a novel method for diagnosis Rotor bar fault under variable condition by analyzing the stator current of three-phase induction motor. The proposed approach combined the improved local mean decomposition for the first time with Hilbert transform to track the instantaneous frequency and amplitude of a faulty component in non-stationary condition. The Hilbert method is used to extract the stator current envelope, which contains significant local feature, thereby meaningfully reducing complex numerical calculation. Then, the stator current envelope is processed via robust local mean decomposition and Hilbert transform for identifying the Rotor bar faulty components. The study results demonstrate the ability of the proposed diagnostic strategy to evaluate the fault severity in detecting the Rotor bar faults by tracking the instantaneous amplitude and frequency of the Rotor bar components. Thank you.
Yep. Thank you. I would like to know if any questions from forum. Yeah, I think there are no questions. And once again, thank you for your presentation, Asma. It was a good presentation.
Thank you.
Yeah. So now let's have a break, and let's join again. Thank you.